greetings. So welcome to today's class. So in today's class, we will ask ourselves the question as to how can one choose the controller gain that appears in the full state feedback controller in an optimal manner. Okay, so that is the question we are going to ask ourselves, and we are going to study what is called as a linear quadratic regulator. Okay. So that's what we are going to look at. So the linear quadratic regulator is a very popular optimal controller, for linear time invariant systems, wherein this using which the control gain k, is designed or obtained in an optimal sense, so as to minimize some, performance metrics or performance index. Okay, so that is the idea behind this linear quadratic regulator. Of course, the name sounds a little bit, say, odd, right? Because if you look at the term of this controller itself, right, which is abbreviated as LQR, so we can see the adjectives linear and quadratic, like coming along with the word regulator, which is pretty strange, right? So because see, we have heard about linear functions, we have heard about quadratic functions, right? So linear function means it will be first order, right? Quadratic means second order function. So how do we use both in the same term, right? So that's something we will figure out as we go along. Okay. So to discuss this, so let us consider the MIMO linear time invariant system. So what is the system that we are considering? We are going to consider x dot t is equal to axt plus dut y of t equal to cxt plus dut. Okay, so this is the MIMO system that we want to consider, and we consider that the state starts from some initial state x naught. Okay, so the initial value of the state is something. Okay, so the question that we are going to ask ourselves is that, like, how do we select this gain, the control gain in an optimal sense? Okay, so this linear quadratic regulator falls under the class of what are called as optimal controller. Okay, so that's something which is important for us to know. Okay, so it belongs in the category of optimal control. Okay, so the question becomes, how do we design this regulator or control? Okay, so that's the question we asked ourselves, and we are going to answer it in today's class. Okay, so let us assume that for this particular system, that the origin is the equilibrium state. Okay, so which is a reasonable assumption. Okay, that's the equilibrium state, and that the realization is minimal. Okay, so what do we mean by a minimal realization? A minimal realization is one which is both completely controllable and completely observed, right? So that is the minimal realization. So we assume that the origin is the equilibrium state, and that the realization that we are dealing with is a minimal realization. Okay. So now what we do when we design this linear quadratic regulator or LQR is the following. The objective is to design a controller that minimizes a quadratic performance index. Okay, so we want to design a controller such that a quadratic performance index is minimized. Okay, so that is the core objective behind the design of an LQR controller. Okay, so that is a very important aspect. Okay, so now if we go back, we will immediately see why it's called LQR. Okay, it is called LQR or linear quadratic regulator because first of all, it is the controller structure is a linear structure, right? Because we are going to have u of t to equal to k times x of t. Okay, it is a linear controller and it is applied to linear systems. Okay, so the objective linear is making sense, right? And it is called quadratic because we are going to get this linear controller by minimizing a quadratic performance metric. Okay, so that is why it's called quadratic. Okay, so I hope now the terminology is clarified, right? Why it is called as a linear quadratic regulator. Okay, so once again, it is called linear because the controller structure is linear, u equals k, and we apply it to linear systems, right? And it's called quadratic because the controller is obtained by minimizing a quadratic performance. So what is this quadratic performance index? Okay, so I'm just going to write down an expression, okay, such that like we sort of like motivate this performance index. I am not going to go too deep into the matrix algebra which is involved. Okay, so that's something which we are not going to discuss here. But however, I am just going to explain the physics behind. Okay, so what is this quadratic performance index? Let me write it down, and then we will discuss each term. Okay, so the quadratic performance index which is chosen is given by this. Okay, it is indicated as J. It is 1 by 2 of XTF dotted with some matrix S times XTF. I will explain each term. Okay, plus 1 by 2 integral T0 to TF X tau dotted with some matrix Q tau X tau. Okay, plus U tau, which is the input, dotted with R U tau. Okay, so this is integrated from an initial time to a final. Okay, so that's what we have. All right, so the performance index has three terms. Performance index has three terms. So what are these terms? Okay, so if you look at this first term, 1 by 2 XTF dotted with S times XT. Of course, how does it work? First, you have this matrix here. We multiply that by the vector XTF, we get a vector, right? Then we take the dot product of XTF with the resulting vector. Okay, so that's how we should interpret this term. Okay, so ideally, we would want the controller to take the state of the system to the equilibrium state, right? And we have assumed that the equilibrium state is the origin. So if I don't go to the origin, I have to be penalized, right? So what do I mean by this? Let's say, suppose we take an example, right? So we have, let us say, a controller that sorts of, essentially, we have a controller, like that, sort of helps in maintaining the trajectory or heading, right, of a autonomous vehicle, right? And we have the position error and the orientation error to be the state variables, right? So ideally, we would want them to be zero, right? Is it not? So that like I have perfect trajectory tracking, right? So, however, in reality, it's going to be non-zero. So, if I were to design a controller, I would want to push those variables to zero. So, this term penalizes the final state. So in case if I'm not able to take the errors in that example, which we talked about, to zero, out of the equilibrium state, I have to pay a penalty, right? So that's what the first term signifies, right? And what do the two terms in the integral or the integrand signify? This term penalizes the state at each and every time. Okay, so not only am I going to penalize the state because of it not being close to the equilibrium state at the final time Ts, we are also going to penalize the state at each and every instant of time t. If it is not closer to the equilibrium state. Okay, so that's what is signified by the first term in the integrand. And the second term, u tau dot r u tau, it penalizes the input at time t. See, we don't want to essentially achieve a control objective by giving too much of input, right? Because there is a cost associated with the input also. See, imagine that, in the autonomous steering example, right? We want to give very high, pulse steering, right? So that's not going to be physically possible. But if you want to realize it, we need very high bandwidth actuators, right? So that's going to increase the cost and complexity of the system. So while we should ensure that the state is penalized and good tracking or essentially follow up of the desired state is obtained, that should be at a reasonable cost, right? So essentially, we don't want to give too much input or realize or ask the controller to realize, control inputs which are non-tractable, right, in practice. So that's why we need to also ensure that the control input is also penalized in some sense. All right. I hope we can understand how these three terms are obtained, right? So once again, the linear quadratic regulator minimizes the performance index. The performance index has to do with penalizing the state vector and the input vector. Okay, so why does it penalize the state vector? Because we want the controller to drive the state to the equilibrium state, which is the origin. Okay, as soon as possible. If it is away from the origin, it has to penalize it. Okay, that is the point. And at the same time, we want the state vector to be driven to the equilibrium state while ensuring that the input is also reasonably small, right? So it should not be very high. So that's what is also penalized or taken as a performance. Okay. So of course, one may ask, hey, why this factor half, right? So this once again goes back to minimization and maximization. So let us say we use some function f of x, okay, which is 1 by 2 ax squared, okay, where some a is scalar. So now when we want to minimize this, we take the derivative, right? When we take the derivative of x squared becomes 2x. And if I choose that half and 2 get cancelled, and then I just get ax, right? So a similar thought process, okay? So that's a convention to essentially ensure that when we take these derivatives, even in this with these vectors and matrices, our that factor of 2 which may come in is cancelled off. Okay, so that is just a convention. Right? So I hope it's clear why that 1 by 2 came into account. All right. Okay. So now, if we look at this particular performance index here, Q and S are symmetric, positive, semi-definite matrices, and R is a symmetric positive definite matrix. Okay, so you can observe that we choose Q and S in a certain way. So what is, of course, all of us know what a symmetric matrix is, right? Symmetric matrix means, like you take the transpose of the matrix, you get the same matrix, right? So that is a symmetric matrix. And if you look at semi-definite and the word positive semi-definite and positive definite, what do they mean? So let us look at this, right? So let me define these two terms. Okay, first let me start with a positive definite matrix. Okay, so what do we mean by a positive definite? Okay, a matrix is said to be positive definite if, let's say, you take the product x dot ax. Okay, so you consider a matrix A, you multiply it with the vector x, which is non-zero, right? So then essentially we have a resultant vector, and then we take the dot product of the resultant vectors, the same x, and if this product finally, which is scalar, is greater than 0 for all x not equal to 0. Of course, this simply means for all. Okay, all right. So then we have what is called as a positive definite matrix. Okay, so typically in many references you will see that the same expression is written as x transpose A. Okay, so as we discussed, the dot product of two vectors is also written as A transpose B. Okay, in many references we will use a dot product as. Okay, so this is a positive definite matrix. So what is a positive semi-definite matrix? So a positive semi-definite matrix is one. Let me write down the definition of a positive semi-definite matrix. Okay. So in a positive semi-definite matrix, we have x dot ax to be equal to greater than or equal to 0 for all x not equal. So please note the subtle difference. Okay, in a positive definite matrix, if x is not 0, x dot ax should always be greater than 0. On the other hand, essentially, if you have what to say, a positive definite matrix, if you have a positive definite matrix, if x is not 0, x dot ax is always greater than 0. Okay, that is one. Okay, but then like if you have a positive semi-definite matrix, what happens is that you can also have this product x dot ax to be equal to 0 even if we have x not being equal to 0. Okay, so that's the subtle difference, okay, between a positive definite and positive semi-definite matrix. Okay, this is the definition. All right. So now coming back to this linear quadratic regulator. In fact, I'm just going to write down the solution. Okay, we will not worry about the derivation here. So the optimal control input, okay, that minimizes J is the following. Okay, the control input U of t is going to be equal to minus R inverse B transpose E, okay, times X. Okay, so this is the optimal control input. So here we can immediately see that this is our control gain K, right? So you can immediately see that the control gain K is calculated from the matrices R, B, and P. We know what R is because R comes in the performance index, right? It penalizes the positive definite matrix, which penalizes the input. We know what B is because B is the input matrix which comes in the state space realization, right? So what is this quantity P or matrix P? Okay, this matrix P is what is called as a solution to the so-called Riccati equation. Okay, so there is an equation called as a Riccati equation. Okay, so and this matrix P is the solution to the Riccati. Okay, so if you go to MATLAB, if you use the command LQR, okay, or if you use the LQR toolbox, you will be able to sort of get the optimal control. So, so I just wanted to introduce you to this, like without going into the details of the mathematics. I wanted to convey that, like there are optimal controllers which will help us in obtaining the control gain K by optimizing certain performance indices. And a common example is this LQR controller, okay, linear quadratic regulator. And this linear quadratic regulator calculates the controller by using the matrices R, B, and P. R analyzes the input in the performance index, B is the input matrix, and P is what is called the solution to the Riccati equation. All right. So that's the introduction to linear quadratic regulator. The reason I wanted to introduce linear quadratic regulators is that, like, because LQR is what to say is a common choice, particularly when you look at what to say controller control design. If you want to essentially look at like even suspension control and so on. Okay, so when we look at automotive suspension control, and we want to control the ride comfort, the road holding characteristics of automobiles, and so on, LQR is a very commonly used controller. Okay, for that. So that is the reason I thought I will just introduce you to LQR and sort of explain what is the rationale behind it. All right. So that is the linear quadratic regulator. Right? Okay. So this is the last topic I wanted to discuss with you as far as this particular course is concerned. So just to recap at a broad level, what we learned in this particular course, we learned various control techniques, both in the classical domain and also the state space domain, right? In the transfer function domain, we looked at the PID controller, we learned about root locus, design based on that, and essentially also frequency response methods and so on, right? And in the modern or state space domain, we looked at the state space representation, we looked at stability, controllability, observability, and full state feedback controller. Okay, so these are some commonly used tools which apply amongst other systems to automotive systems also. And nowadays, with the problems, even in the automotive domain becoming non-linear, right? There are also like other non-linear control techniques which are applicable. Okay, so but we have restricted our scope to linear systems, okay, in this particular course, because still there are many problems where the model is either linear or approximately linear or linearized from a non-linear mode. Okay, so that like we can apply the concepts that we have learned. Okay, so these concepts are pretty useful in practice to design controllers for physical. Right? Okay. So that I will stop the theory discussions for this course with this topic. So if you have any questions, points of discussion, please feel to discuss them. Okay, so if not, I'll stop recording and I will end this session and our theory discussion for this course. Okay, thank you.